Thank you. I appreciate the opportunity to share the work that we've done in underground mining with our evaluation of the heat generation from our diesel and our battery electric vehicles. What I'd like to do is highlight the motivation of the study and explain the tests that we conducted, and then go through reviewing the results and discuss a bit of the conclusions that we had. As we're all aware, the momentum continues in the trend towards battery electric mobile equipment in the underground mining applications. Such a trend is driven by the desire for the workplace environment to be free of diesel particulates, reduced temperature and humidity, as well as reduced noise and vibration. Economically, there's a significant value proposition with the reduction of ventilation infrastructure and operating expenses. Our study is intended to help quantify these benefits and share actual application data from our underground evaluation. We all know that the battery electric powertrains are more efficient than the diesel engine powertrains. And given that the electric motor is 3 times more efficient than a diesel engine, one would expect approximately 3 times less heat production. However, this is not really the full story. This theoretical value does not account for the differences in the vehicle construction, such as the pumps, the hydraulic system, regenerative braking, torque converters, etc., all of which have complex solutions to solve. This places the emphasis on the importance of field measurements of electrical vehicles as their adoption becomes more prevalent in order to provide a more real-world comparison and assist with the mine design. We set out to test the battery LHD and the same size class diesel LHD in the same environment. This would help us quantify the actual heat differences between the two vehicles. I'll also note that we were able to capture some of the energy consumption data that I'll share with you a little bit later. Through the collaboration of our partners with Glencore, our dealer Tormont Cat, and Hatch, we were able to establish a test procedure for this side-by-side test and evaluation. The test was carried out over a 2-day period at a Glencore mine in northern Ontario, in a heading that they had of approximately 1.4 or 1.5 kilometers below the surface. During that time, we were able to complete 3 runs of the battery LHD and 2 runs of the diesel LHD, containing several cycles within each one of those runs over that 2-day period. The battery LHD was charged each time after the runs, and what we did with the diesel LHD is exited the heading for the same period of time that it took for charging so that we could have comparable cycles. This chart depicts the high-level comparison between the traditional diesel LHD and the battery LHD. The R1300G with its 3306 engine and the battery LHD was equipped with fast-charged liquid-cooled batteries, providing both machines with the equivalent output power. Each machine carried 7.5 tons and ran a straight route of approximately 107 meters long. The hydraulic pump was driven on the diesel machine by the engine, and versus the battery electric machine had its own independent drive motor. Then there's the mechanical torque converter on the traditional diesel machine and the electric motor controls on the battery. Both machines were outfitted with onboard data logging systems that we were able to retrieve later to capture a significant amount of performance data. This graphic depicts our layout of our battery electric machine. Our test bed, we removed the engine, transmission, torque converter, the fuel tanks, and replaced them with primary components such as the propulsion motor, the pump drive motor, inverters, batteries, and a new cooling system designed for the battery pack. Majority of these components are installed on Caterpillar machines that we have in the market today or have significant validation hours on them, and were integrated into an optimized system by our development team. Given a view of the cycle that we ran through here, we started out with a brake test at point number 1 there, just to mimic entering in mucking the muck pile. Forward tramming to the simulated dumping area, and then stop to lift and lower the bucket for a bucket cycle at the end, then reverse back up to the original location. The cycle is repeated probably about 26 to 30 times in each run. And notice that there's an elevation change there, approximately 10 meters long, that did give us a bit of a drive regeneration downhill. The heading was empty of any other equipment or personnel at the time, and there was a simple auxiliary air supply duct that provided ventilation. So the team conducted 2 primary measurements: energy input to the LHD and heat input into the ventilation airstream. The objective was to measure all the energy entering and leaving the heading in the airstream, identifying the change in heat that would have been generated by the LHDs. Additionally, the team took some manual spot checks along the heading to be sure that the data logging equipment was accurate and validated. The lower image is the upstream sensor located in a hole in the supply in the ventilation air duct, and the upper image there is the downstream sensor located just beyond where the dump cycle was on the heading. So each of the average runs were about 7 minutes, or 70 minutes, sorry, and intended to do 3 runs for both LHDs. We only were able to do 3 runs for the battery electric LHD. The day we did the diesel test, we had cage delays, which happens in the underground application. So we were only able to get 2 runs during that day for the diesel machine. Average tram speed was kept roughly equal during the 2 days of tests of each machine. And then I'll draw your attention to the note relevant to the minimum airflow. During our test, the airflow was at 13.4 cubic meters per second. This is quite high, and it's about 80% higher than the regulatory requirements for Ontario for the application of these machines. So I'll point back to that a little bit later. After completion of the testing, the data logging instrumentation was removed from the machine, and a plot of the air temperature leaving the heading is presented in the chart you see here. We chose to show the wet bulb globe temperature because it captures both the wet bulb temperature and the humidity that's in the air. This gives more of a realistic feel that the operators, the workers in the section actually feel, as opposed to doing dry temperature alone and wet temperature alone. The 3 battery electric runs and the 2 diesel runs can be clearly seen with each run exhaust profile. As the LHDs were doing each run, you can see the gradual increase in temperature, and then as it exited, the decrease in temperature. You see that the magnitude and the difference in the temperature is quite significant between the chart on the left of the battery and the right of the diesel. Now, if you recall that the airflow was quite a bit higher than the regulatory requirements, this is something to keep in mind, because if it was set actually at regulatory levels, this variance, this difference between the 2 machines would have been quite a bit more than what you see here. So that basically is implying that the benefits of the battery electric LHD is probably a bit greater than we're actually presenting here. So we once again highlight the theoretical ratio of the 3-to-1 seems to underestimate the difference in the heat output. You see that there's approximately 10 times more measured total energy input of the diesel LHD than the battery electric LHD. There was a significantly lower ratio of the airstream input than the measured energy input. You see by the center chart there, roughly 7.5. And this indicates that not necessarily all the heat reported out to the air. More than likely, some of the heat would have been captured absorbed back into the machine itself or into the rock walls of the mine. So that's probably somewhere else that would need to be measured for any future testing. But we were able to witness the wet bulb globe temperature ratio of 7.5 times more than the diesel machine, as opposed to the 3-to-1 ratio that would have been calculated from the electric motor efficiency. Now, this is very case specific and would have been impacted by the amount of humidity, the airflow within the entry, et cetera. But this was the case that we had of those two exact machines, one diesel, one electric, in the exact same heading and same environment at that time. So in addition to the other workplace benefits and the expenses related to ventilation and refrigeration, it was beneficial for us to consider the total cost required for the diesel and the battery machine's operation within the same duty cycle. Looking back at this simulated cycle that we saw before, we've superimposed on there the battery consumption profile with respect to each of the duty cycles. The machine starts at 0.1, trams with a slight downhill regeneration to 0.3, and then reversing back up to its original location. Considering the typical costs of diesel and electricity in Ontario at the mine we actually were testing, we saw a 10 times reduction in energy cost with the battery machine, which is a pretty good story. Note that this is representative of only the cost of operating the machine itself, excluding charging. So that would have to be considered when you're looking at the whole cost impact for the electrified mine. Total energy input to the LHD was calculated for each vehicle based on the recorded status of the charge, and then obviously the fuel consumption within the diesel machine itself. So in conclusion, the ratio of the diesel to the battery electric LHD heat loads are significantly greater than the expected 3-fold increase based on the efficiency of an electric motor calculation. We witnessed the 7.5 times variance. And this amounts to millions of dollars, both from an operational standpoint and CapEx for a greenfield site. When comparing to a diesel mine, the reduction in ventilation requirements achieved similar workplace conditions either allows for a reduced ventilation rate for the same productivity, resulting in significant CapEx and OpEx savings, or an increase in mine productivity and throughput for the same ventilation and cooling intensity. Additionally, we observed energy costs of 10 times less for the battery LHD given the equivalent duty cycle. Further testing is recommended, but we hope that this strengthens the validity behind the industry's justification towards electrification. There are clearly benefits to both the greenfield and brownfield operations. And through our studies, ironically, we're finding that by electrifying the underground mining equipment, we're actually helping our partners reduce their electric bill. So with that, thank you.